How many of you have started loading your data, your neural data, and trying to get a look at it? And has anyone come into any problems originally? The link, and I've just put it under the announcement from yesterday.
Oh,
Yeah, it's fixed now. I forgot the comment of things twice. So what kind of problems does anyone run into, if any, if you've started to load your brain data and try to model it? Have you found explanations to be clear, or I fully imagine that it's been a bit tricky to figure which library to use to load the data, and is it out of date, still maintained, and what sort of problems have you been having? Or are you just waiting for the coding workshop to do that? Yeah, totally understand. Okay, so we're going to look at 3 things today, and we don't get time to go through all of them then. I've written a set of notes to sort of explain what's going on in each cell, so you should be able to work through that have on, and then send me an email if you have any questions about that. So starting up with EEG, fMRI, and then with large language models. And just to, if you are going to reset the notebooks and run once, there are some cells that download the data and make some changes, and if you try to run them again, it won't work. So at least for the initial downloading and creating things, just keep those only run once. Otherwise, you'll feel stuck in your boy. So what we're going to look at today is a data set that was recorded, 2004, 2005? And it was looking at the question of how the brains process faces when they're intact, and also scrambled versions of the faces. So this is originally from the SPN toolbar, so you can see an example and scramble. It's the same statistical information, but it's been jumbled up for the face and see an intact face here. So they did an anatomical MRI scan, they did some functional MRI, as well as EEG and MEG. So because nobody's chosen to work with an image data set today, we're just going to look at EEG and fMRI. We'll load the data, have a look at whether machine learning can tell us whether or not it's possible to classify a difference, and sort of what tools and libraries, mainly in Python, can be used to get a better visualization. So these are some of the techniques and some of the functions that you might want to call, or at least be inspired by, to get a sense of how to do some analysis after you get some results, and how to do some nice plots that are being a super final report. But first of all, I just want to introduce the whole idea of face processing in the brain by face illusion. Has anybody heard of the fact-check illusion? I was hoping not many people are enough. That seems to be true as well. The idea is, if you look at this photo from down, it's upside down. It kind of looks normal. Everything kind of seems like, this looks like a photo of somebody taken upside down. But as you look, well, obviously, because it's denoting as an illusion, you see, you turn it upside down, it's actually the reverse image. So what does this show us? What does this show us about how the brain processes faces? And so, like I said before, this goes back to a fair while ago. This is a report in the Guardian newspaper that talks about the origins of this experiment and what it teaches us about the visual system. So it was originally done for Margaret Thatcher's, and you can see, you can tell that both of the faces are different. But they don't look like one of them would turn out to be a monster if they turned upside down. But in fact, that's, as you can see, when we process faces that have the inverted features, so the mouth, the nose, and the eyes, the right way up, it's different from how we process them upside down. And so the clues are to the visual system, as you can see here. It shows that by and large, faces are made up of the same consistent features, eyes and nose, mouth. But we process things holistically. It's not just the sum of the individual elements altogether. Otherwise, we should have been able to recognize the upside-down versions as being particularly odd, because they wouldn't, align with our expectations and our previous experience with viewing faces. So, yeah, the fact that we don't suggest that we process and recognize faces in more of a holistic manner. And so that leads us into what's known about how the brain processes faces and what signals can be detected from neural data. So what the Thatcher illusion tells us is that there's something special about face processing, and one very common result in EEG research is this effect called the N170. The N170 is what's called an ERP, or event-related potential. And this shows that if we treat an event as like when you're presenting a stimulus and over and over again, and if you have people who are responding to faces, then typically what happens is there's a negative effect you see in the imagery approximately around 170 milliseconds after processing a face, and it's a very, very robust effect that you can also see in MEG. It's clearly got the M170 for M for magnet. And so that's one thing that we're going to look at in the EEG data. So the idea is you have multiple presentations of faces and multiple presentations of the scrambled versions of them. And so if you can align everything to the onset of the presentation and then take the average of the EEG signal for one condition and then another, if you subtract one from the other, what you get is the net effect afterwards of what is the neural response to the difference in the conditions. So the idea is what you always want to do in cognitive neuroscience experiments is to find two conditions that you want to contrast and have them as equal as possible and only manipulate to the feature of interest that you want. So the idea is that's why we're not just taking any scrambled images, the scrambled versions of the faces in the data set. So there's no new information, there's no new contrasts, there's no new colors. And then these scrambled versions, it's the same image, the same set of image faces, but if they're scrambled. So if we want to click through the lovely ad, the first little book, I'll show you some things that you can do with output. Okay, so we start off there. Don't know all the type of data sets that people are doing EEG for your project, so what formats that they will come in, but quite likely you might come across the EDF format, EDF or VHDR, VHMK, EEG, and all of these relate to different brands of EEG acquisition systems. So there are many companies out there that each happen to have their own way of formatting with all this stuff. So. But there is one Python toolbox called MNE, and we're told some of you about it as well. It's had its origins in frequency encephalography in terms of trying to work out what's called the minimum norm estimation, and is then developed into sort of a general purpose electrical signal from the brain, but also from the body, and how we do process and basic machine learning. So if you don't have to run any yourselves, if you just want to follow through, you'll see the output. Some of them do take a long time, so you might be out of sync, so I ain't gonna run anything okay, but it should all work if you want to go through it and start experimenting a little bit. So yeah, we would download data from the SPM website and we'll zip it. And this is just a lot of preliminary processing. So first of all, you can see here from this read raw PDF, we know that they're looking at the brain, so the biosensing EEG recording which has its own features. And so it comes in two sessions. So session 1, session 2, it's just the participant has a break between, and then they look at another set of scrambled versus activate first. There's some extra pre-processing that I had to do here just to remove some channels. So you can see in the original download, there's a REGUI file which has basic information of how many electrodes we can expect and what was done, and kind of other information that might be useful in terms of what the stimulus files contain, because that can be a bit tricky as well. So we have 128 EEG samples sampled to 2048 hertz. Plus we have the electrodes on the earlobe, right earlobe, and we have electro-optograms, which are electrodes placed on the eye. So one of the things that you'll come across when you're pre-processing data such as EEG and MEG is that the eyes are basically dipoles. They're a positive and a negative end, and as you blink and as you shift your eyes, these send the electrical activity to the brain, and it's often a much higher magnitude than the effect that you actually want to record. So if you're processing faces or something, so if you could record from when the activity is happening, it helps you better remove the effects of the eye movement in the signal later during pre-processing. That should be something that I think a lot of people consider as just like a viewing task as well. But once we have the eyes closed and maybe you're just doing imagined movement, then it's not necessarily as important. And I know some of you are doing that, motor imagery or so. but that I don't think it'd be too important, but it's practice you would say if you're reading a ET preprocessor not for paper. So then we have this concept of the montage. So we load the biosemi 128 electrode montage, and this just shows the distribution. So we have the ears here, and this triangle which is the nose, somewhere looking down on the subject, and it's not sort of exactly the relative placement of each electrode has a label, has a name, and this is approximately where you would expect to see. So, we know from visual processing in the back of the brain, or eye movements at the front and by the nose, and motor cortex around here. So, this is useful, but when you want to start labeling your signals, because you can come up with I'll show you in a second how to plot, where you can see each signal has a color which represents where it is in the brain. So, sorry, the montage. So once we've loaded that data, we can call, you can call the plot and the question mark function in a notebook, and it has this nice facility wording. And the function signature will pop up, and you'll be able to see all the different ways that you're able to manipulate a plot in order to make it look nice. So we include a different set of electrodes. So if you are really like yourself, then study the function signatures of these libraries, because you can often do a lot more than you probably think you can do with the. And then to call plots, we have you can specify that we want to start, say 20 seconds in, and we want to plot in duration of 5 seconds. So this is what it looks like, the raw data. So as you can see, we have the A electrodes here. Obviously, we can't fit LG28 in them, but you can see them where it's being plotted here. It's the ones at back brain. And then, so this other signal looks like. So, the way EEG is recorded is a difference in two electrodes. So one we call the reference electrode. So ideally, if you put an electrode in the middle of a room, there's a lot of other activity going on, electrical interference. So you want to have sort of a baseline that's recording everything that the other electrodes around the brain is experiencing as well. And you want to subtract that from what the electrodes on your head are recording as well. So the idea is that if the reference signal is containing the noise, and then you just want to subtract that out, then ideally what you should have is only brain signal, going into the other electrodes, because you can't have a way to just have the neural activity recorded, because it would still gather everything and interfere with everything else that's going on in the room. Whether that's the body signatures, they could be a lot of things. But the problem with having a specific electrode is, ideally you want the relationship between that reference electrode and all of the electrodes on the head to be equal. But because you have different sets of proximity, so you have the reference electrode on the top of your head, and you're considering another electrode very, very close to it, we know that the way the electric signal hits the bone and scatters out, and there's a lot of spatial correlation between different locations on the brain as well. So the relationship between that electrode very close to the reference and one a bit further away is going to be different, and that's not ideal. So we take the average of the entire signal we record for each electrode and just subtract it. So that does have the potential to introduce some noise of a different type, but it counteracts the fact that the spatial proximity between an electrode and the reference one is there, so it makes it kind of more fair. And that is simply done just by, we can call the set reference, and the reference channel being the adjunct. So in the data set as well, what you'll find is the stimulus channel. So when you load the data, we would find those extra electrodes that we dropped, or those extra channels, and at the electro-oscillogram, they would have the 128 temporal series of the electrical activity recorded. And then in another channel, we would have what's called the stimulus channel. But it's a way that as you have the amplifier, and as soon as you're presented something on screen, you'd send a pulse of electricity through the amplifier, and it would record in the same EEG system that, okay, the experimenter has told me that something of interest happens here. This is how we time lock the ongoing electrical activity to the experimental events that we're introducing. So what you can do is, after you've loaded your raw EEG data, is what's called MNE find events, and then this would go through, find those pulses, and then say, here we are, I found an 72 loop. And what's happened in here is that they're all of the same value now, but there is a mapping times, so we can recover the information later. Sometimes we're saying more modern snake recordings, you would just directly send a 8-bit value, and that would determine which of your experimental categories should be in here. This is the sample in the EEG data. So if we know the sample frequency and we know that say this thing happened at sample 45,837, we can work out how many seconds after we started the recording that this event happens. We can ignore the middle column for now. It's often not even some. So if we wanted to find out when exactly the third event happened, we can say that we would go events 2. So remember, Python is 0 index. So if we call the second element, we're actually getting 0 first, second, actually the third one. And we can look into the loaded EEG data object, and we take up the parameter, S rate, sample frequency, then divide one by the other. So the third event happened 15 seconds with 0.4 seconds. If we want to load the condition labels that come into this data set as well, simply we send a text file, split the lines, and I print out the first 5 elements here. So we scramble, the spaces, scramble, space. So now we just need to do a little bit of correction to put that in the data format that would allow us to do such a later analysis and machine learning later. So because of this, we're going to map faces to 0 index and scramble to 1, and then we're going to replace all of those zeros and ones, or faces to scramble with what the index code is. And we can see here, once we print out the same first 5 events, we've now replaced this 6, 5, whatever events, and now we have binary X code to say scrambled face or whatever, or is real. It's a trace. So you should be able to see here, because we have scrambled as 1, and we know we've scrambled face, we should expect first three should be 1, 0, 0, and that should be fine here, 1, 0, 0. It's always worth just making sure, if you're doing this for the first time, and just make sure that you can go back as many times as you like, and figure out, does this make sense? And I have a list of the text of what's being presented here, and here I have my colleagues just always go back, because you make a mistake on this and kind of invert it as well. It's a bug that wouldn't show up as an error, but your analysis would go nowhere, and you might be stuck for a long time until you really go back and just think, it could have been so much easier to just go back and check every individual step here. So an important step in the EEG processing is also filtering as well. So if we take the power spectrum of the EEG data, we can see we have all of these signals, and so each element along the x-axis here, it's a frequency component, and we can see how see a few of them spikes. There's obviously a lot of them there that and it's not relevant to us typically in cognitive neuroscience. We're only interested up to about 120 hertz, because anything after that is, it's going to be related to noise in the environment, or mechanical, or other electrical interference. So this is why we filter the data. So just to plot where I said what we're interested in, like typically 0 to 100 or 0 to 120, this is the area that we're interested in. And you can see a spike here at 50 hertz. Does anyone know what that might be? So it's the electrical hum of all of the electricity, all of the outlets as well. It exists everywhere. So different parts of the world run at different frequencies. In the US and Canada, you're on 60 hertz, so you would always see this, that would be a peak here. In Europe and in Eastern Japan, so there's a weird thing about Japan, where Eastern Japan uses one set and Western Japan uses the 50 or 60, because when they were setting things up, I don't think they really thought too far ahead, and it became too costly to be able to unify the whole country. So different electronics work with different frequencies. You can imagine it's a mess for EEG comes across Japan for this. So you will always find that this is an effect that we want to take out. So if we are interested in anything going on in the brain at around 50 hertz as well, the electrical activity in our environment, unless you're in an electrically shielded room, this would interfere with it. So we can apply what's called a notch filter here. So this would just be to take on the very specific notch of the frequency band that just before, below, and just after 50 hertz to try and remove the electrical activity from, we would say, the warp socket and things like that. But that's basically done just by, I've made a copy gauge because filtering is a process that's like destructive. It's not something you can just take away. So in case you want to go back and play around with an earlier version, I've just put this copy in here. But basically, we're calling the filter function and we're specifying the low band and the higher band. This specific call is just to take away everything above 100 hertz. As you can see, not everything happens instantaneously. Filtering is a process that works and it's very continuous. You don't really have any disjointed edges, and you can't just have a signal sort of drop away. So even though we specify that we want to filter after 100, we'll start to see the drop afterwards around 120. But we still have that 50 hertz into the year span. So this is what we can just call notch filter, frequency at 50, and it will remove it. As you can see, you don't really have a full perfect line as well. There is an effect of applying the notch filter because nothing is perfect from the technologies that we use, but we have taken out the effective electrical noise. So we wouldn't see that as an interfering factor in better analysis. The next thing is epoching. Now this is different terminology than what you might be used to in machine learning or deep learning. So an epoch is typically one whole pass through the data if you're working with mini batches, but in EEG or when you come to do our sense, what I mean, it's a window around an event. So you basically know the mean. So what you have here is a long continuous signal from the start of the recording until the experimenter you turned off the machine, basically. And what we want is a sequence of trials around these onsets of when either faces or scrambled faces were presented. So this then goes to some epoching, which means we take the timing events that we found, that find events function, and we would extract a window of interest that we're interested in using, which will do some analysis, some machine learning, wherever we might be interested in. And this is just, so at the end of this, we've been using this raw EDS, like data structure in MNE, but we want to start working with some claim. So we're passing in the filtered EEG data, the events that we found, we're specifying in relation to the onset time equals 0, we want to take a small window beforehand, and we'll explain why in a second, and then take up to 70 milliseconds or 0.7 seconds from the EEG response. And this then converts the data into something that's a bit easier to work with. So as you can see here, once we just call the epoch's result, it's mapped there 172 events. We have a time range from 0.1 to 700 milliseconds with a baseline interval from 100 milliseconds before and then afterwards. So you might be wondering, why did we extract information before the signal? Because obviously the brain hasn't seen the photo yet. But what we find is gradually, if somebody is sitting there, especially on a hot day, the electrodes might start to lose connectivity. There could be a different sort of profile. You can see a lot of low frequency trends. There might be a systematic offset. So if we were to just take the epoch version from the raw data as well, we could find that one presentation to the face at the end of the recording session could be very different from the one before in terms of being shifted by however many microvolts. So what we do is it's got a baseline correction. So as we're looking at each data window around a stimulus onset, we want to take, it's typically 100 seconds prior per channel, take the average of this and just subtract it. So we're using the baseline interval to take the 700 milliseconds and then correct it around 0. So there's no systematic offset here, but me centering the epoch here. Typically, when you have this part of the epoch data structure, whenever you're plotting, whenever you're doing any analysis, MNE will like to apply this and then not actually physically or even destructively change the data. But you can also apply baseline, which will make a change and then you can drop the baseline, but then there's no way to recover things again. So you would settle way we want to do that, we'll be fine. You just have to remember that if you don't cut it away, you want to then extract it into like NumPy format or anything for deep learning applications, just be aware that you might also be extracting the baseline period, and therefore when you want to specify a very specific time period, you might be off by 100 milliseconds. So that's something to be aware of, which should be your own pre-processing. Yeah, we can see that now we don't have the separate events data structure around. It's actually just tied into this epoch events and called shading. So we have 172, which are the 86 intact faces and the 86 scrambled bacons. And we have the condition map that we defined earlier. But if you remember, we looked at the original data and it had a sampling rate of 2048, which is very, very, very high temporal precision, but far too precise for what we want. And one of the things we're going to look at later is fitting a model at every time point. And so it's going to be very computationally intensive to train 2,000 plus models. So we're just going to downsample the data, which is going to make it 250 hertz. So every second of recorded data is just going to have 250 separate time steps, separate points in the matrices. This will make some of our computation go a bit easier. So yeah, we can call it the sample function. In order to do that, you'll specify the new frequency, and then this is updated in here. So RS space is just resampled, and you see the new one is 250. So to recap what we've done, we've loaded the raw data from the experiment, which is downloaded automatically in a notebook from the dataset website. We extracted the events. We used the separate condition labels to update stimulus information in our data structures. We've filtered the signal. We've got rid of some of the noise in terms of that 50 hertz electrical buzzing. And then we've extracted a time window around each of our presentation consents and then downsampled it so it's more computationally efficient to work with. So at the end of that, we have 172 elements here. And yeah, we can look at how many in that third column were 0, which is our presentations of an interface, or 1, which is a scrambled placing, say 86 makes, so let's make some the 172 events we have. In the box data structure, the actual data values are stored in this memory variable. And so typically what you'll see is hyper, and it's associated the way that the program is. If there's something that begins with an underscore, it kind of means you shouldn't be calling this yourself. Other functions in the library will do this as well. It's kind of protected, but if you know what you're doing, then it's just an easy way to access data. And yes, you're basically experts on EEG analysis or here, but see that bang. So now we look at the representation of the full data. So we want to take the temporal information of the shape. So actually, yeah, the first shape here, we have 172, so however many experimental events happened. We have 128 electrodes, remember? And then we have 200 time points for each event. So because we did some downsampling, and it was 250 hertz, but we know we only extracted 700 milliseconds after, but we also have the 100 milliseconds before. We had 200 data points here. So yeah, just call this and then multiply by 1,000. So yeah, we can find that we have 800 milliseconds of data here. So because we changed the label of the condition map, we can very easily just call into here, say we need faces, we want scrambled, and then we can just call the average function over there. So what this is the determining epoch data structure in single kind of evoked array. Not important why it has that name, but these are now many data structures that represent an average signal here. So we can call a plot function, and if we specify spatial colors equals true, because we set the montage earlier that showed the relationship to the location and the name of the electrodes, it has a nice color map here, so you can see light green and yellow represent electrodes at the front of the brain. We have a nice blue and purple around the center, and they darken above around the bottom as well. So you can see here we have our baseline interval, here is where the faces were presented. Then we have a very strong reaction positively at the back of the brain, followed by a dip afterwards, and then as the data goes on, there's a lot of randomness in the data. We haven't fully done a lot of signal cleaning, so it doesn't look as great further away you go from zero. But that's not the portion of the data signal that we're interested in anyway. So here is the plot for scrambled events, so the easier response to scrambled faces. And so, as you can see, it's quite different. We know that the N170 has a very strong effect very well, and you can replicate it here. And so, what we want to do here is we want to take this signal, the average of all of the face events, and then we want to subtract from it the average of the scrambled events. And so, look, we'll see what happens here. So there's a good function to call here, which is called combine evoked. And we specify the weights here as 1 and -1. So we will take the first one and subtract from it scrambled average. And here we see that subtraction. So if you think about it, you have the response to faces, which we know generates this N170 effect. And then we have scrambled faces, which we don't suppose generates the same effect. You subtract one from the other, you're going to end up with a net negative effect. And as you can see around here, we start to see this between 150 milliseconds up to 300 milliseconds to like exactly in the area that we're interested in. So we're doing minimal pre-processing on this open data set, and considering the question of the EEG responses to faces and scrambled faces, we just replicated the result finding the N170. And because we have the data in this format, we can then start to do some machine learning classification on this as well. One function that we call on this combined difference, this plot joint, and this will take the main top 3 events it thinks are significant, and it will give you a nice topography. So topography is just here, the spatial layout where red represents positive electrical activity and blue represents negative. So remember we were talking about the N170 is a negative effect, and as you can see in the data that we have here, it's found at 168 nanoseconds, so very close to what we call the N170. We can specify a lot of different parameters to here, and if we're not interested so much in the later part of the signal, we can just call what we want our time min to time max to be, and we can specify where we want to see the spatial topographies of the electrodes afterwards. So here I've specified 0.7 for even 17 milliseconds, and you can see, as we saw in the purple response here, it's at the back of the brain. So as you might remember from some of the paper presentations we were talking about the FFA, this is exactly in the back of the brain. So we also kind of understand that it makes sense from what we know of the literature and what the brain areas that respond to faces, it all ties up. In order to do some classification, we can extract the data from using the get data function, and this would give us the same array of 172 by 128 and 200. And so MNA has this nice decoding package. I'll have a link in here about the whole decoding tutorial, and this is mainly taken and slightly edited from the we can make a pipeline which scales the data. And so this then is different from what you might know or have experienced within scikit-learn from standard scaler, which would naturally start to scale the time points. We want to scale the effect of the electrons over time, and so this is what the MNE version of scalar will do. We want to vectorize the results, and we're going to use a logistic regression classifier here. And I'm going to call cross-validation multi-score on our EEG data here in X, and our labels, which we have just extracted from here, just showing that the column of the epoch events. And we can see here, okay, we're able to score 82.6%, but the effect that we saw was clearly visible to our eyes as well. Anybody would be able to say, okay, but then what you have to remember is it's in an average result. So what's going on here is we're actually going down to the single data point level. it's obviously a lot more noisy there. If you were to plot a single instance of a face versus a single instance of a scrambled face, there'd be a lot more noise, it would be a lot more tricky. So, but we know using that entire window, the logistic regression classifier is able to work with that. What we can also do is we know that we're interested in more in the 100 to 300 millisecond window. So if we make X2 here, we can take a subset of that time window, which represents 100 to 300 milliseconds, and we actually run the same thing again. We can actually boost the score up to 88.4, which just means that there's a lot of signal in the later part, which is being recorded by the EEG, but we know it's not in response to the conditions that we want to contrast. This is just other things going on in the brain. It's just adding an extra noise. So finding more of a tight window around the area that we expect to see a result will often boost your scores, and that's something to keep in mind for your own project as well. One thing that we can do that's really interesting, but this has the requirement that classifiers need to be quick to fit as well. So what we did just before was we had the entire window we got was 82% accuracy, but then we tightened the window around what we were interested in. The area, the temporal zone of 100 to 200 milliseconds, and we found that we could boost that accuracy. If you take this to the extreme case and we only consider single samples, and we fit a model at each of those time steps, so each of the 200 time steps, to solve the same problem, when we reach a point where the classifier is able to extract useful information from the signal, we should start to see a boost in accuracy. So what I'm going to show you here is it's called temporal decoding. So here we have the baseline period. We have a lot of noise in here. There's classifier period. It's hovering around chance, and then around 100 milliseconds, we start to say, okay, there's some signal in here in the EEG data, which is enabling us to get good. We're not using accuracy, and we're using the areas of the receiver operating characteristic. And then once we get to around to our region where we expect similar results, this 100 to 70, we're almost at perfect classification. But then you'll notice it drops away again, which is what we expect, but we also see very high retained signal, not as strong as what we find in that period of interest, but there's an open question as to what is the information in that time period that seems to be related to doing a good prediction of scrambled lists and scrambled faces. Things I left out are, there's a method called independent components analysis, which is a way to find, so you deconstruct the data and you would be able to identify various components of noise and you zero them out. That requires a bit more expertise and understanding of what goes on in the brain and what kind of source of noise is. So I've left that out, but you might want to consider reading up on that if you have especially noisy signals. There are a lot of data quality checks that you can run in MNE. You can run automatic detections for bad channels, which may be like the connection between the electrode and the head is loose, so you're just getting noise, it's not really responding to anything. People also do a lot of bandpass filtering, so you might find for specific cognitive effects, so you're interested in, or maybe you've like for motor imagery, this has been shown as well that you don't want to just have, say, 0 to 100 hertz. You might only be interested in specific frequency bands, and there's a lot of research in that means that you take the power of the bandpass filters and use those as features instead of using the raw electrical activity. And I've left the question of the deep learning thing up to you, because like I said, I wanted to show temporal decoding. You can't really do fitting of X61 models very, very easily, especially not in the time for this class. So I'll be glad to you. So now fMRI. How many of you? Yes? Yeah, so it's like you're taking the matrix of a time section, so you've got a 2D matrix of this time set and you're running a model, and you're dropping the score into a list and just moving on and fitting it, and then you're just plotting the results of those scores. Or you can think of it as 200 different logistic relations on size. I see. Yeah, that's probably the more intuitive way to think about it, yeah. Okay, so there's a lot of just things that you might need to know for fMRI pre-processing. We can't go through a lot of them with the time that we have, and I also don't know whether you have used data sets that come very nicely processed for you, or if you would be expecting to, or if the data comes in a format where you might need to revisit some of these steps. So as we acquire an fMRI time series, the person is sitting in the scanner and there are slight head movements. So the first step that we want to do is realign them. So basically, we pick an image that we want to represent a specific set of time while the subject is in a scan. We call this a run in fMRI. So how many runs does you get a recording session? Many runs as well. So here you can see in this image the flag out in place. So we would run a realignment in order to try and minimize the spatial transformation to be fixed, to try and make it such that if an electrode, if a voxel is here and it has been shifted over, then we'll be able to realign it so that as we look at the time series of voxels, they represent the same area of the brain, or also the same not area of the brain if it's outside the head. We're doing, it's a sequence of 3D tensors, and so the brain only encompasses the small part of that, so there's a lot of places where we didn't expect to find any activity, and especially around the edges, which just happens to be the cortex, which is what we're often interested in. It has the tendency to introduce a lot of noise, so it's very important to consider that step. The only other one that talk about is co-registration. We're not going to do co-registration here, but typically when you're acquiring a lower signal, so in order to do time series fMRI, you have to sacrifice a bit of, quite a lot of spatial resolution as well. If you want to do a structural MRI, then this usually takes about 5 minutes or so, and you can get a very, very detailed picture of the brain, just what say here from one of plus views. But for fMRI, if you want to acquire a whole volume every 2 seconds, we have to make some sacrifice of the spatial resolution. And what that means is they're aligned to different spaces, and we often want to plot our results that we find in terms of structural MRI that is acquired as the person is doing the experiment. So typically, on the side your releases you're going, you sit for the structural, what's called a T1 scan, and then you would go on to the experiment which against T2 images, which are the fMRI time series there. There's many other steps to this, but what we're going to look at here, you need to consider about the realignment step, which is also called motion correction, and then co-registration to a structural image fields. In terms of machine learning, there's an idea that was much more popular a few years ago that isn't so much now in such books with deep learning, but it's this idea of what's called a search light. So if you imagine you have your torch or flashlight to say, okay, is that right? You say torch like us,
we say flashlight here.
So it's just like having a searchlight anyway, a portion of the light is highlighting an area of the brain. So typically there are too many voxels and there's not enough information, say a single one that might be representative, but typically you want to just look at an area around the voxel. So it's like, if we're interested in this area of the brain, we would open up the searchlight and we would consider all of those voxels, we would fit a machine learning classifier, and then we would do the test on held out data, and then we would move it along different areas of the brain. So we'd have a feature matrix, we would fit a model, we'd have a map of an accuracy. So but here, you can imagine the one voxel in the center of the brain, and then we would take a radius around there, consider those voxels as input features for a machine learning classifier, and then in the very central one, we would mark the accuracy for that voxel. So it's not that every voxel in the searchlight gets updated with the accuracy value, it's just the center one, so each voxel has the result of being tested on in the training data, all of those features, and then you have separate brain data which you use to calculate your accuracy. And I worked a little bit on this in my master's thesis, and I was looking at different machine learning classifiers and the sensitivity to, I think it was like the semantic representation of concepts that are alive versus like objects and tools and other artifacts as well. So considering in the temporal lab, I was predicting, so the radius is 3 voxels and plotting the results of the classification accuracy, so comparison between SVM and also Gaussian phase. which somehow suggests it has some good properties to when you're working with multi-subject data. There has to be kind of aligned to the same space, but so how it's a written column. Okay. So we are going to call the download function for the same website. I'm just going to select it right at the time. I'll just actually show it to you after, in case you want to download it on your own laptops or something. So it's just click here on, so we have the easy data that we downloaded before. We're just about to download this one, and also the structural data as well, because we want to be most useful to this parameters. No, let's go. Session 2. So we need a few different libraries. We're just going to install these here and load the data here. I'm not going to go over in the cells book, which talks about what file types typically come onto the scanner, and sometimes we need to do conversion to the most common modern format for fMRI is called nifty. Well, nifty images, and we just have the .nii. So if you have a lot of single images, so like different scans, there's many in the downloaded data, and so each individual 3D matrix comes to its own file. We can actually just combine these, and we typically have like a 4-dimensional tensor, so you have 3-dimensional tensor of a single acquisition of a brain volume, and then the extra dimensions just tag, and it's much easier to plot the values, temporal values go on through there. So once we've done this, basically the images that we're going to be working with here, we're going to look at the shape here. So we have the 4-dimensional nifty image. So we have 64 by 64 by 32, which is, so yeah, 64 dimensions and 64, and then along this dimension, so imagine my head is in the scanner like this, we have 32 dimensions here. I'm going to go through some of the different terminology that people use to look at different orientations of the brain. It's got, should be on this code. So, so we can call this get f data, and we on this nifty image, and so each single brain voxel is, and that just brings up an example of the first data sample here, which is all zeros. Does anyone have any idea of why they're all zero or what it could be? Yeah, so they're like brain area. It's like, so what you're going to find is, you're probably in the top corner and in the bottom corner at the other end, and the brain is somewhere in the middle. So we have a lot of zeros for the areas that aren't the brain. Specific slice of each dimension, and we can plot it here. So this is like very noisy. One of these images, and we can see, so the view from brain can be either this side on, or this side on. So how I remember them typically is that the coronal one, so corona means crown, coronation, and coronavirus, like there's crowns in them as well. If you imagine a crown on your head, but it was sharp and you just pushed to the face, and what would be revealed as the part of the brain you'd be looking at head on you. So that's how I remember the coronal view. And the axial view, you can just imagine someone taking an axe and chop off the top of your head as well. So you peer down and you get this view of your head. I never really figured out a way to remember sagittal, but I always know it's the one that's not the other two. So each way that you look at the brain has a different view. So you'll see often different views and what they're called. We can call locked image function on these nifty images that we've loaded as well, and this would show us what's going on in a specific location. So we have these black bars here, so in terms of one view where this location, the back of the brain here, and what it looks like from the coronal view here. And it tells us the activity of what's going on at this specific moment in time for this specific functional image. There is also so we can call the cut coordinates, or we can provide the cut coordinates to the function call, and So now we're going to ask for what is defined as the center voxel. So as you can see here, we should space. If you're not using a Jupyter notebook and you can call this, it's usually got a lot of interactive ability. You could just click on your mouse and move around. I was going to try and show an example of that, but I didn't have time. But by specifying the different coordinates, you can replot and see what's going on at a specific pixel image. There are some functional calls that are more specific to specific types of fMRI data that be recorded. So you don't really need to know this, but it's what's called EPI images, so equiplanized imaging is a type of method of recording functional time series data. And so what you have here is interventional, so higher activity, we'd expect to see a lot of cerebrospinal fluid, and this has different properties. So what's recorded from fMRI is different from a lot of places in the brain. So this just helps you say, okay, considering that we are using EPI images, if this plot reveals a lot more of contrasts that might be of interest to us. We can also plot the structural image that we downloaded, which is here. So, and I said before, because we don't have any temporal dimension to this, we can spend a whole 5 minutes to record this one 3D body. Whereas if you remember, for functional time series data, we're trying to capture a whole 3D image in 2 seconds. 2 seconds, 5 minutes, it means we get a lot more spatial resolution. And so, and we often want to plot the results that we get from functional data onto structural data. We can do this motion correction step. So what we have here in this first 4-dimensional time series, I think this method by default takes the first image and then it goes through all of the rest of them, and it tries to use that information to create a single affine transformation to apply to the whole of the brain data, try and make everything aligned as smooth as possible, so it corrected for the motion of subject movement in the scan. That takes quite a long time to run. But what we get to that is this corrected in the 4D image that we get. So I've written a function here to plot time series of one voxel in the brain. So I've selected this 0, 0, 0 here. We found the beginning, and to be much, we have this 4D time series, and see it's virtually 0, and so as that fluctuation happens. The reason is because we corrected. There are multiple different ways you can correct motion correction. You can either pick the first image of the sequence and try and align every one of the subsequent ones to that image, which means the more movement that happens that accrues over time, plus the variant, it might get a bit worse of an alignment, but it should be okay for the rest of them as well. So, as you can probably guess, this is not a brain voxel, so this is why we don't see much of interest in time series. If we plot a different one, and this time I'm also going to plot the spatial location of what we're looking at again. Like here we are with, as you can see, the coordinates that we specified. It's maybe a bit difficult to say here. Yeah, it's in the corner here, and this is why we're not seeing any activity in recorded or any bold activity in this voxel. But we can specify a more central voxel. So here we are. Now, so this is the bold value recorded at this specific location across the time series of fMRI data. And we can see if we've got some information here. Is equal to learning a classifier for things non-vectors? We don't know yet. We have to do some more statistical analysis. But one thing I wanted to point out here is we're still in the very center here, so we're not actually back up on the cortex where we expect to find something. We're in the middle of what could be a ventricle. So obviously properties here of the bold response might have to be different. So let's try again and pick this one somewhere. So here I specifically try to find one where solids that have more activity given by the Galilean. As we can see, the magnitude of bold response is greater, and it slightly increases, but it's a lot of noise. This is what typically we have to work with when we're doing these classification of temporal data and fitting these models. So what I'm going to do here is going to try to come up with a brain map. So usually there are specific developed special software that you can't really easily load into Google Color. So we're just going to do a very, very crude thing here is we're going to plot a histogram of the bold values across the whole image. So that take the whole time series and look at the histogram of what values we find. And you can see all of the ones outside the brain are going to be these very low ones of, and if I just specified, we'd eyeball it and say, let's do a cut up of one of the groups. And so what we do here is then we would take all of the brain data, mean it across the axis, find every voxel, it's over 100, and that's going to cancel off range. So we plot this. This just means that when we have a lot of results like that we want to plot backwards to the structural image, it's going to ignore. I mean, it's not going to be perfect, because as you can see, this is just a very, very crude step, but this is how we're able to come up with a basic version of the brain master to only allow results that we know from the brain into our final analysis. So we're not going to discard registration step, but that is probably an option if you are working with fMRI data and you do have to go through these pre-processing steps. That's a very useful thing to do because they cuts will come on us more nicely, but you have the downside of that it's going to resample it to a much higher spatial resolution, and at least when I tried to run it on my laptop, that didn't have enough memory for it. So yeah, we just have to usually find the jack or listen to also learn. So compute kind is nice too. So similarly with the EEG data, we have these trials. It takes a little bit of time to figure out what's going on, so you have to load them. This was in the MATLAB file. Obviously because SDM is a MATLAB program, so it took a little while for me to just figure out what to convert all of this. But basically, what comes through the headers, we find names, onsets, and durations. Here's the names. We find faces, we find scramble, because face first one. And MATLAB is not zero indexed, so first element of every array is 1, not a 0, so we just have to correct for that. Just something if you are working with data from MATLAB files and you are transferring it up to Python, you can't just take the absolute value of the index because things will be off. So we're going to remap 1 and 2, 0 and 1, and then print the onset times of each. So here we are. So we know that 7.6 in the temporal sequence of faces present. The next time a face presents was 12.394, and in here we have the scramble takes it. So what we do with this event information then? By reading the documentation, which is really, really important. So I first thought these was a time event, so that these represent in seconds, but after I went back and had a look, the people of data actually said, no, this is in terms of units of scans that you have. So actually this says somewhere in the 83rd scan, we find an event here. I mean, try to go off, so just have to be careful, make sure you read all the accompanying information, even though it might look like something that you think makes a lot of sense. Like that's for me, it was only because some of the numbers didn't add up that I actually went back and revisited it and figured out what was actually going on. So just be careful of that. Also, make sure you're always plotting what you expect. So remember in the previous case with the EEG data, we had 86 normal faces and 86 scrambled faces, but what they've done in the fMRI classification is we have 64 face classes and 86 scrambled face classes. So the classes are not full, which then has implications for model training, for what is your chance accuracy, because obviously 50% accuracy is only valid when there's an equal balance between classes. So often other metrics are more beneficial when you have this class imbalance. Another step, what you would like to do, because fMRI data is very noisy and we have correct promotion, and we know that voxels that are in very similar spatial locations often have a lot of properties that are the same as well. So by smoothing, we can recover and boost the signal to noise ratio. So if you were to look at an image of it, it would look maybe a bit more fuzzy, but the idea of not having this rapidly changing voxel noise values in a specific area, it's more than likely due to some pre-processing effect, or it could be an error. So smoothing is exactly that would often boost your signal to noise ratio. I'm going to skip over the scaling here and just get to the analysis. Basically, we're applying standardization. If you remember before, we had so many voxels that had, its value say 1,425 and in others 840. We have to correct for this by doing a normalization debate. Otherwise, anything systematically different, the magnitude could be affecting the linear models that we need to take into account. So some features don't dominate over others, and everything's sort of on an equal playing field. So if you remember when we talked about fMRI, we also had the problem of the hemodynamic response function, which was that information recorded in fMRI takes between 4 to 6 seconds to actually show up in the data as well. We have the scan intervals of exactly when the target presentations happened. So, like that, if you read some tutorial about to do fMRI pre-processing, they have many, many more advanced ways. What I'm going to do here is show that we're just going to add 4 to our timing on 6. And so if we do that, we had originally had, say the first 2 here, 7.8, 12.34. Now this is going to be 11.8. We've just added 4 to this value. And because these represent the units of scans, we can use those. But the C812, which just means any number that's not a whole number, you just take the immediate integer higher than that. And then that is going to represent the exact scans of the temporal sequence that we would fake. And so here we are now for faces, for scrambled. These are the scans that we're going to take to include in our analysis. We want today to split and shuffle the data as well, and break in a few important assumptions here, because the fMRI has this thing called temporal autocorrelation, which means that you often need to be careful about how you split the training test data. Just for this simple analysis, I'm ignoring that, so we can't trust the results that we'll see. But what we're going to do here is we're going to import as a linear support vector classifier, and similar to what we saw in the EEG data before, we're going to call this RC, the Rocket EEG score, which has a property of being a correct metric if you had a balanced classes. So we also used it in the previous case, we did use accuracy there. More important that we use a method that's sensitive to class imbalances here. So yeah, around this model's going to test data at 80.8. So we're actually doing pretty well at detecting using the entirety of the brain, or the brain boxes that are in the brain mass that we calculated. But because we only have such limited data, we could do run this a few times, you'll start to see vastly differing accuracy scores. So it's sometimes lower than 0.5, which is chance that area in the curve score as well. But because the pre-processing has been very low, we've only included one series of data. We haven't done much other correction as well. We still find that I ran this, I think, for 50 or 500 originally, and just plotted this distribution of what we found. So basically, some of the scores we put below 0.5, but the bulk of the ones we're finding are correct classification. Also, there is overall signal in the data, just in order to run this notebook. Essentially to give you a sense of how you should always report results over multiple runs, so you get an idea of how variable your estimate is. And then what happens then, we can take so because we've been building a linear model, each voxel has its own set of weights, and we can extract those and plot them back on the structural image. So here I am doing thresholding, and it's also not co-registered, which is why it seems a bit odd. You can sort of see how the time series of the functional one to sit over there. It's not quite exact, but these are the length weights for each voxel in the brain. If you do get a really good classification score, then you should be able to set a high threshold value. So here I've just changed it a little bit, and then you can pick the ones that maybe sit in the most positive, the most negative, and you should be able to see an area of the brain that is more responsive to the area in question. They say this is not expecting to find recovery of the FMA and with these limitation, lack of standard pre-processing, but this is to show you what is possible. You can also plot this back on functional image, see where these are, and there are a few resources over here. Right. Now to large language model until the last bit. This last session is quite short, so we should be able to finish it for next time, please. Okay, if you haven't heard of this company called Hugging Face, basically a long time ago, transformers were ridiculously complicated to try and get working with. They involve a very tricky model loading, and in order to get things to be used, lots of people use the standard codes that were released by Google and misunderstanding a lot of it. And so what Hugging Face did was so as transformers really started to take off, they kind of simplified everything. They made a really great book, lots of video courses, very, very easy to load and get the results of large language models. So if you are going to work with any X representations, I highly suggest using I'll show you how to load some of the data, how to extract some text embeddings, and some other considerations that you need to be aware of when taking raw text that may have been provided with your project data. One thing that I just want to mention before we look at the code is what tokenizers. Has anyone done NLP? Does anyone know tokenization and what? Do you want to have a go? Just a quick explanation. Yeah. So what we used to do is we used to define a vocabulary. We used to go outside for English. A common value was 50,000, and we would have Moha vectors where one would be selected in to indicate whether it was one word, whether that word was in there, and then we moved to the old sort of vector space models or text representations, but we still had to define in text, for specific words. And so that meant that we were with a fixed vocabulary then, which is unideal. So it means that a lot of, say, new language wouldn't be used, any spelling mistakes. It just means that we would be unable to get a sensible text embedding for those. And so the various other options of tokenization have happened. So one was, like, say, the extreme other level is the character level. So you would go through an entire text, you would make a representation for each individual letter and punctuation symbol. And so different models have different tokenization schemes. What we've ended up landing on is this sub-word tokenization. So we're not using the full word, we're not down at the character level, we're taking common small chunks, and this is how words are split up in different markers. So let's try and make the So yeah, very, very simple to install plugin breaks. So just click install transformers so that it can view. I also have a book called Natural Language Processing with Transformers that explains how to work with plugin breaks. They also have a very, very good beginners course online. The links to that are in the very bottom, so I definitely recommend checking that out. And if you want to borrow my book, then just let me know. I'll bring it in to the advance for you. So this is just a demonstration of some summarization. So I took one of the abstracts for one of the papers that somebody presented. Here's a wig book for face cells, and asked to do a classification. It's very easy to choose to specify a task, given your text, and then here in the summarization, want to turn this abstract into these results about face response in your serpents. But that was just for a demo. So BERT is one model that you might have heard of. It's what's arguably the first LLM. Well, yeah, maybe just moderate size. It stays world of LLMs. And so this is a tokenizer, which we can call from here. So BERT tokenizer from transformers, from pre-trained, and you'll be able to specify a model name. This just means that it's case sensitive, and it's what's called the BERT-based model. It's one of the BERT's rules to be introduced. And then we can define a sentence in a variable, since this is one string here. And then we call tokenizer on that sentence. And what that gives us is a dictionary, again, which has these entries, input IDs, compensate IDs, and attention. And the one thing I'm going to focus on here is just the input IDs. So in terms of the fixed vocabulary that each LLM has to have, this is just telling us what index we go to find the initial embedding that we then click to the transform. So in the sense that if your sense of machine learning is great, it's giving us this sequence numbers as well. And if we start to decode, then we can see what is going on here. So CLS token, or the class token, is a representation at the end of the transformer that's useful for doing downstream classification. Often you just want to take embeddings for specific words. We can ignore this. We can also ignore this separator one. This is just a carryover from how BERT was trained. We can also specify, so these add special tokens keeps false, and means that we don't get the response to this the CLS token or the separator token. But one thing I wanted to point out here is that when it does the tokenization, we found that for a lot of the words, it's just selecting the word itself, except in neuroscience, it's split into any hash euro and then hash sign. So this is to indicate that there was an original word that doesn't have its own embedding, and we split it into these subunits, and each one of those subunits will have its own embedding. But the library is clever enough to be able to reconstruct the whole sentence if you ask it to. So if I put this back in, now you can see tokenizer when it wants to be coded. It's actually just connected neuroscience again because of the way that the subunit components are encoded in there. So if you are loading a lot of text and you put it to the tokenizer, you might notice, okay, I have 10 words in the sentence, but I have 15 text embeddings, and that's because you'll be getting the representation of the subword tokens as well. If you want to get the actual text embeddings from BET, for example, then we will use this. We can put the BET model, get the info IDs, and it's just basically called hidden state. We have the 768 dimensional vector. I have some examples of this. Is the example for the 6th layer of BET at the first position, the first 25 tokens, but it's the 11th word. And also, as just an example, we can use GPT-2, which comes with the rephrase transformers library. We can do exactly the same thing. It will just download we tokenize different sentences. You can see the tokenization here is different. It means it's a different scheme, and this is what time it has split up. It hasn't got any of the words actually. It's just sub-words as well. But then I tried to come up with the sentence where I knew that it was being deep into tokenizer. So yeah, class course, I had a great class, and best office out there in mathematical things such as they put these into these little chunks here, and I've expected it showing this by the indentation that's during the subword here, so like it's at the start of it. So if it doesn't come across a word, it'll try to split it up and draw text embeddings for the sub words, which kind of is a bit like the word trace method that we used to have in character base, and this just is the way that best of both worlds, let's just say. So yeah, that's just to show how the GPT tokenized effectively. And one minute lets you go, so just allow me to do the extra bit. Yeah, I just wanted to say that ask us if you get stuck with any of your data pre-processing. It's a very, very tricky set of topics, and I think it's very easy to fall into some traps. So if you felt more at ease by checking things with us out, just send me an email. I don't mind responding to those. But also, you look into the literature with keywords, try and get some novel ideas. If you see something in a paper about something that you want to test, then I encourage you to try and implement it if it's not too much. And especially with your assumptions and not very familiar with neural data. So I would say apply the defensive coding principle. Like, just list the assumptions as your data is coming in and out of functions. What do you expect about it? Everything that you just assume to be true. Write an assertion. Make sure that things are the same thing. Is the number of events equal to the number of rows in this? Is the temporal sequence that I found it here, does it match here as well? Always just try and put that in. It's going to save you so much time, and you'll quickly recover where your problems might lie as well. And also, I know it's going to be very stressful, but it's like machine learning with brain, it's very cool. Do enjoy the process and just realize that it's something fun to do, and you'll be very, very happy with it. So right out of the foot. Probably will be a lot of stress and challenges, but don't lose sight of the fact that you're actually landing something really cool yourself. Coding. Right, thank you everyone today. I have my office hours at +1 to +2, so you'll see me then if you have any other questions. Sleep.